I've used from him, an example of using proof by induction in the context of mortgage payments. Well, that's all I'll say. But introducing like your first concrete example of a proof by induction, that's me saying it because I think it's easier, right? So this and well, the next two squares, this square and the first square of the next session is. And a little bit, yeah, so the next two squares are me, right? Okay, so what is induction? Well, the basic idea is now proof by induction. Again, you've got some mathematical statement P, and you're trying to prove that it's true, okay? Now, induction tends to get used when your mathematical statement P has a kind of parameter. It's about some integer, n, right? Where n is some natural number, let's say. Right? So your mathematical statement P is some function of n, where n is just some natural number, like 1, 2, 3, whatever. Okay, and you're trying to prove by induction, this particular technique, that some formula for this statement is true. Okay, so when you use proof by induction, you'll have some kind of formula for P, and that formula will involve some natural number, some positive integer, usually. That's the usual context in which you would use a proof by induction. Now to make that may sound a bit vague, but to make it clear, I'll give you a concrete example, and maybe that'll help you understand what proof by induction is about. So you're trying to prove by induction that some formula, they call it P of n, is true. Right? So P is some mathematical statement about this integer n. Now I'll give you a concrete example now to help clarify this. Let's say this statement here is P is it's the sum. Let's say the sum of the first n, little n, natural numbers, counting numbers. So in other words, 1 plus 2 plus 3 ... plus n. Okay. So that's the meaning of P. Right? P. So in this case, P is the sum of the first little n, first n natural numbers. In other words, 1 plus 2 plus 3 ... plus n. Okay. And now here is a formula, like a compact formula for this sum. It's just this, right? So in other words, if that's true, P of n, which by definition is this sum, but its actual value, the formula, is this, right? So in other words, P of n is this. Now that would be, P of n is this. That would be your mathematical statement, right? So you would then need to prove that P of n, which is defined by this, the sum of the first n natural numbers, is equal to this formula. Right? That would be your theorem statement. And to actually prove it, you use proof by induction. So I hope that's clear. You can have all kinds of different things. So P gets defined somehow by, I don't know, some kind of math, and that's equal to some formula of some sort. And then your theorem statement would be P of n is equal to whatever this formula is. Right? This is just one concrete example. And you then have to prove that that's true. And to do that, you use a two-step process called proof by induction. So how does it work? And we'll use this as the vehicle, the means to show you how it's done. Right? We'll use this concrete example step by step to show you how to do a proof by induction. Right? Now, as I was saying, it's a two-step process. So first, you prove that this is equal to this formula when n is 1. Okay? So you show that P of 1 is true. Okay? So and that first step is called the basis step. It's like the starting step. Now you'll see why in a minute why it's like the starting step. But that first step, prove that P1 is true, and that's called your basis step. And the second step, sort of more important, that's usually the harder one of the two steps, is you assume that this formula, whatever it is, you have to be given the formula. You can't do induction unless you have some kind of formula, unless you have some formula for P of n. If you don't, well, you can't even start. Right? That's the downside, the negative side of proof by induction. You have to have the formula to start with, and if you don't have it, you can't. Then proof by induction, you don't have any proof statement to start with. Right? You have nothing to prove. Okay. So assuming this formula is true for m, okay, integer m, right? You then prove that it's true for n plus 1, when P of n plus 1. So you assume this is true. That's an assumption. It's called the inductive hypothesis, assuming that this is true. Now, if it's true, you then prove, and that's step 2, step B, that P of n plus 1 is true, like the next integer up. Okay. Now, can you begin to see how the two connect now? Maybe starting to click and crystallize. So now, assume you've proved these two steps. Now, so you've proved the basis step, the first step. You've proved that it's P of 1 is true. Okay, and you've proved this one. That if P of m is true, then P of n plus 1 is true. Okay, well if m is 1, now we know P of 1 is true because you proved it here in the first step, in the basis step. Right? So if P of 1 is true, well, since you've proved this before, that means that P of 2 is true. Right? Because if m is 1, see, that means P of 2 is true. Now you've proved B is true in general, for if P of m is true. Now, if P of 2 is true, put m as 2 now, well then P of 3 is true. And if P of 3 is true, then P of 4 is true, and so on. Okay? So you've proved it for all positive integers, all the natural numbers. Okay? So that's how you prove something by induction. Alright, so now let's actually do it, and I'll use this this statement P with this formula as an example of an actual proof by induction. Okay, so you're asked to prove that the sum of the first n natural numbers is that in other words this. That's what you're asked to show. The first big N natural numbers is given by the formula, P of n is big N over 2 times n plus 1. Right? That's what you're asked. You're asked, like, that is your theorem statement that you're trying to prove. Okay? And, well, it's the next session, but it's a proof by induction. So there's always two steps in such a proof, an inductive proof. The basis step, so you prove that it's true for n is 1, big N is 1, and then you prove that if it's true for m here, it will be true for n plus 1. Okay? And then with that logic, if it's true for P1, it's true for P2. And if it's true for P2, it's true for P3, and so on. Okay? Then that logic clicks in. Alright, so the next session we will prove that it's true for P1 when big N is 1. And then we'll do the second step, proving that if it's true for Pn, then it's true for P of n plus 1. Okay? That's how you prove by induction. So next session we will do those 2 steps for this concrete case. Right? It'll give you an idea of how it's done.